And if there is a temperature difference, you don't have to do anything, heat will get transferred. Right? It's an automatic process as long as there is a temperature difference. Very simple concept that some students, when they look at more complicated system, they tend to forget that, why is that heat that's transferring across? What is that that's pushing heat over from the hotter side to the colder side? There's nothing pushing that. You don't have to do any work on it. As long as there's a temperature difference, heat will get transferred. So heat transfer is thermal energy in transit. So there is this T part, T word over here. In transit due to spatial temperature difference. That's a formal definition. Spatial here just means in 3D space. And you can see that part that I was talking about, as long as there is a temperature difference, you get heat transfer. And this part over here in transit tells you a very important parameter. When you see in transit, that means it relates to time. It relates to time. And that's why for heat transfer rate itself is also relating to time. That's why you get a unit of watts. Now, things like kilowatts, if you break that units down in terms of joules, what will you get? Kilowatts is equivalent to kilojoule per second. So that second at the bottom, denominator over there, tells you that it relates to time. Tells you that this heat is transferred and there is a transit process. Time is taken to travel from hotter to the colder side. So we said this is heat transfer rate. So later on we're going to hear more about that, some equations, governing equations behind it. So heat transfer and thermodynamics. What's the difference between that two? In this module, I was trying to figure out if you were to go to Glasgow and if you would take that 4-year degree course over here is only third year, fourth year. If you go Glasgow and start from year 1, your year 2, if you were to do that over in Glasgow, you would take a module that's called thermodynamics. Over here, you're on the third year. Advanced extending due to all the right now. So thermodynamics extends on that you have heat transfer. So if you were to take thermodynamics, you'll find that thermodynamics is about the end state here. And very often we use the word equilibriums. Right? So in equilibrium state, so equilibrium means that there is this transit of heat, and after a while things settle down. And then after things settle down, there's no more heat transfer, and you achieve this equilibrium state. Thermodynamics gives you that. Unlike for heat transfer, we look at the transfer of thermal energy from one place to another place, and that another place is going to be from a hot to a cold temperature. So this is the difference. Right? One is talking about equilibrium, thermal equilibrium, thermodynamics, and the other one talking about heat transfer, heat transiting from hotter to colder. That's the main difference. So there are tons of applications around for heat transfer. You wouldn't actually need to look far. Just look around you to find heat transfer. The air conditioning will be one. Your body is actually another one. Now it's still too active. Yes, it's still too active. This will catch your attention. I know that will work. So me do this. I only do this with hands. Let me do this. So stay close with me. Don't drift away. Stay very close with me. Don't drift away. So some of the examples listed, for example, the oil rig, where you can find heat transfer. In fact, heat exchanger, where heat exchanges between the hot fluid and the cold fluid. That is a perfect example where we have heat transfer going on. So aircraft, I was talking about this last year. So have you ever wondered, okay, now I'm back. This is the only way. Okay, I was talking about this last year. If you imagine the aircraft, do you think the aircraft is going to carry air conditioner, what we have down here? Air conditioner system to cool down the cabin, the aircraft cabin. The aircraft cabin will still need to be cooled down, even though it's high up, flying high up in altitude. You wouldn't be using the external cold air up there in the atmosphere to cool down the aircraft. There's not a way to cool it down. You will find that your aircraft is thermally insulated. And yet, where's the air conditioning come from? Somewhere they're providing this air conditioning. So actually, what happens in the aircraft is that they don't bring the entire air conditioning up there, put it in the aircraft and fly it. What they do is something that is kind of like what innovative. I'm not sure, have you played with an air pump before? So the air pump would, if you were to pump it, the air that has been compressed actually gets off. Compressed air. You could imagine it as a lot of air molecules in there. When they're compressed against each other, right, there'll be more of this heat that's generated. So compressed air will become hot. So conversely, if I have compressed air and I release it out, that release of that compressed air cools down that air. So compressed, heats up, release, expansion, cools it down. So what the aircraft did was pretty ingenious. What they did is that they don't bring an air conditioner up there because air conditioner is heavy. So what they do is only to bring an air compressor. So this air compressor would compress the air, and this compressed air would naturally get hot. So this hot compressed air, what they did next is to pass it through a condenser. The condenser is to pass the outside ambient air, up there is pretty cold, pass it through and cool down this hot compressed air. So after cooling down this hot compressed air, that air in there will be cooled down, and yet it's still compressed under high pressure. Cooling it down doesn't change its pressure because it has been compressed. It's just after compressing, it's hot. So cool it down. So now you have cooled down compressed air. What they do next is to release it. So when you release compressed air, like I was saying just now, that air expands, and as it expands, it cools down. That is your natural air conditioning. So that's how aircraft deal with it. And they don't bring air conditioning up there, but they use this property of compressed air and air extension to provide your air conditioning. So they can mix with the air that's coming from outside. That low temperature air is supplied with air extension. So that kind of heat transfer is also found in aircraft. Your automotive is also another area that you're going to see heat transfer. I was looking around some video clips, I was thinking, should I show you a car engine that catches fire? It's too hot. So what is happening over here? There is fuel that's pumped in, and that piston is going to come up and compress that fuel. Your ignition spark plug will spark it, and as it sparks, it will explode, and then that piston is going to be pushed down. As it pushes down, it will run your wheel, and it's going to come back up. And as it comes back up, your exhaust valve is going to open up, and that combustion air would be channeled to the exhaust. So there is a lot of heat that's transferring, and a well-designed engine will require a certain amount of cooling because you have that fuel that's exploded, so there's a lot of heat that's generated. So there's also another application that you can find. Last week we were talking about electronics. All right. Please don't think that as a mechanical design engineer you will never deal with electronics. Your second year, there's a dedicated module. It's called microelectronics in consumer products. So you'll be having that. So you still need to deal with electronics. So some students were wondering, I'm a mechanical engineer. Wait, I'm a mechanical design engineer. I design mechanical things. Why do I need to deal with electronic stuff? These are EEE students. They are electrical students work. Why am I there? The reason is because nowadays a lot of mechanical components require microelectronics to drive them. We can't have a physical means of driving it. We need to control the motor in order to deliver the kind of output force, acceleration, or velocity that's required. So no longer mechanisms is sufficient. It would still have its place. It's just that more and more increasingly, we have a lot of this microelectronics knowledge that's coming in to help us to drive mechanical components. That's why your motor has there is that. That's why your degree there is that microelectronics. So last week we saw this electronic system, talking a little bit about the cooling fins. So over here you could see that cooling fins, and on top of it you have a fan over there. We'll be talking a little bit about this sort of cooling where you will have forced convection. Another area is manufacturing. Now in manufacturing you experience a lot of welding process, a lot of heating up process. It could be mold, that injection molding. So you need to look at what kind of thermal properties your mold would have. How do you prepare your die set in order to have your mold in there? So there's also that sort of heat transfer knowledge that's required. I have a few projects working on renewable energy. In fact, next year you're going to have your final year project. I'm going to post out some final year projects, continuation of some of your seniors' work in renewable energy. So just to share with you some of the interesting ideas over there. So I have students working on how to harvest energy that is vibration. Now you would have learned in your dynamics control. You started that, dynamics and control. So it talks about vibration. Now if I have a cantilever that I can design and place on this vibrating source, and design my cantilever such that it will resonate under that vibrating source. And when it resonates, I can have a piezoelectric material. This piezoelectric material will harvest that flexing energy and convert that into electrical energy. You can find this kind of material in a flat panel speaker. Right? They use the piezoelectric material. The the fact that my laptop could be so thin and yet has a speaker in there, it uses piezoelectric material to produce that sound. So I have the students to harvest energy coming from vibrating source and to design the kind of cantilever in order to maximize the amount of electrical output out of that vibration. And we would want to heat its resonance on. So that was one example. Another example that is commonly found in the industry, in renewable energy, is when you have these concave mirrors. Now the job of the concave mirrors is to focus the sunlight onto a pipe. What is in that pipe? That pipe, you would have fluid that's passing through it, and as it passes through it, that pipe, this focus solar energy, the light energy, focusing on the pipe will heat up that fluid. That heated up fluid can now be used to do work. It can be heated up that so much that it will turn into steam, and when you have steam, you can use that to push the turbine so as to produce electricity. Or if you don't heat it up that much, but just to warm it up, that warm fluid can now be channeled as, for example, for your heater, water heater that you have at home, that can be stored in a heater tank for later use as well. So there are those kind of heat transfer that we'll be looking at, particularly looking at the convection. Now, so this lecturer recommended 2 textbooks. One would be the Holman textbook that we have bought. And if you want another opinion of textbook, you could look at what it used to be this as a first author. So what happened is that this author passed away, and these 2 guys were good friends. And this guy is pretty old now, and he's handing over the book that they created to these 2 new guys over here. That's so because they have some academic standing in heat transfer. So it used to be called this Incorpora textbook during my time, but now Bergman seems to be the lead author for this textbook. But in any case, this is another opinion that you can get if you want to have another textbook. This one that we have bought, if any of you still require this Holman textbook, because it's no longer on a physical sale, you can actually go online and purchase it. So if you're still interested to get a copy, let me know. I'll pass you that website so that you can order it online. It's done by the same publisher that you met here. Now, it's not necessary to always go for the latest edition. In fact, I look back 4 editions ago. Most of them are still more or less about the same. Very frequently, what they do is correcting the errors or add 1 or 2 more chapters. So, Glasgow, they delivered the heat transfer in 2 ways. Unlike in Singapore over here, in Glasgow, it's taught by 2 lecturers, one about conduction, one about convection. So in 1 week, they would have 2 lectures. For us, it's 1 lecture, 2 sessions, 2 hours. Over there, 2 lectures, 2 different days, 1 hour each. And it's taught that way every week. Right? So conduction for 1 hour, another day convection, 1 hour, that way every week. So that's why you get to see my lectures over there. Because 9 weeks. After 9 weeks, the 10th week, we will have revision, and the 11th week, we will have something. They are able to do this because they have also tutorial sessions designed over there. Over here, I try to add the work example discussion into the lecture, so we don't have like a dedicated tutorial session. But that doesn't mean that if you have any needs of tutorial, you wouldn't have anywhere to go to. speak to me. Very shortly, I'll be uploading the set of tutorials for convection. Normally, what I do is to time it such that you have learned the material so that hence you could now attend the tutorial. The set of tutorials that has been uploaded for convection actually comes together with radiation. So please only attempt that set. It's one single sheet. First part of it on production, second part of it on radiation. So please attempt your production side first. And after we've covered radiation, then you could look at radiation. So in Glasgow, it's broken up into conduction, radiation, and the other lecturer doing convection and heat exchanger. So we'll be doing this first, or we have done that already. This is second, third, and this is fourth. In that way. Why that way? That's because radiation has its own set of cycles that happen to coincide with conduction and convection. So it will be confusing if I deliver it in that way, because I want you to have a good closure to conduction and convection before you go into radiation. And heat exchanger over here requires knowledge in conduction and convection. So 1, 2, 3, 4, and that way will be the best. Now these slides sort of repeat what we have heard already. It's basically talking about if you have this surface here that's at a hotter side, and then the other side over here that's your ambient, you will see that the temperature will drop. The temperature will drop across in that point. So this is your x-axis, this is your temperature axis. So this part here, T1 is greater than T2. So this temperature at the wall is higher than this temperature T2 out in the ambient. I want to talk a little bit about this symbol over here, right? Q, kind of like double prime. Could you see? Q and double prime over there. Q and double prime over there. So this symbol, Q double prime, is actually called heat flux. And heat flux would have the units as kilojoules per second per meter squared. That's the units for that. This is actually equivalent to kilowatts per meter squared. That's a heat flux. Whenever you see flux, flux relates to the surface area. That's what is per, as well as per surface area. The one that you have seen so far, we deal with Q, that is called the heat transfer rate. And the units for that is kilojoules per second. Or you can just write kilowatts, right? Because watts is joules per second. In some way in the textbook, sometimes you might get to see Q dot. In fact, Q dot in certain textbooks, not Coleman, other textbooks, they use heat transfer rate using the symbol Q dot. This dot over there represents rate. If you learn your dynamics and you see dot, it means per time. So some textbook would write instead of Q over here, you would write Q dot. And some other textbook, instead of writing small letter Q here, they write capital letter Q. So different textbook uses different symbols. Q dot in our case is heat generated per unit volume. And that would have the units of kilojoules per meter cube. This is volume, unit volume. In our case, capital letter Q, we just call it heat. And heat would have the units of kilojoules. So this part over here with this units, you could look at it, it's actually equal to Q over A. Because Q here has a unit of kilowatts, area meter squared. So this Q prime, double prime, is actually equal to Q over A. They are equal. So you have heard about conduction before, which is mostly talking about heat transferring in solids. Although it's actually not only limited to solids, you can have conduction in liquids as well. It's just that if you talk about liquid conduction or liquid heat transfer, if you talk about liquid heat transfer, you get mostly convection more than conduction happening. It doesn't mean that convection is only for liquid. So you can have in liquid flow the process of convection coming in, that's dominant. There's also a little bit of conduction happening. And for your last stage of radiation, we'll be looking at how heat can be transferred without any medium in between. We've heard conduction requires some sort of solid, that is your medium. Convection requires some sort of liquid, that is your medium. Without solid, liquid, or gas,